In this lesson we're going to look at the Haber process. The Haber process is used for the industrial manufacture of ammonia, and we're going to be discussing this apparatus here in front of you. But before we do that, let's have a look at the all-important equation for the production of ammonia. Okay, you'll see straight away that it's a reversible reaction, and so we're going to be taking in some important considerations with regard to the conditions of this reaction and the design of this apparatus so as to maximize the yield of the ammonia produced. But first of all, let's just have a look at where the nitrogen and the hydrogen come from for this reaction. So we've got nitrogen coming in here, and we've got hydrogen coming in through this channel, and the ratio of nitrogen to hydrogen is as the molar ratio in the equation. Okay, so it's 3 to 1, 3 moles of hydrogen to 1 mole of nitrogen. Now the nitrogen, well, there's plenty of nitrogen available in the air around us. You'll remember that 78% present in dry air, and so we're going to obtain that nitrogen from the fractional distillation of air. And you can watch the video on this process in the section on atmospheric gases. Okay, so that's where our nitrogen comes from, and the hydrogen, well, that can come from one of two processes: either the cracking of alkanes, which we've looked at in the organic chemistry section. So for example, the alkanes will come from the fractional distillation of crude oil, and they're heated at high temperature and pressure to produce alkenes and hydrogen. Or for example, from the reaction of methane with steam. So you've got methane plus H2O. Okay, that's water in its gas state, steam, and that produces carbon monoxide and hydrogen. Okay, so two possible sources for hydrogen gas. So to understand this apparatus and how it works, we need to consider ways in which we can affect the position of equilibrium of this reversible reaction so as to maximize the yield of ammonia. And you'll remember in the previous two sections we've been looking at Le Chatelier's principle, and it is Le Chatelier's principle which we are going to apply when designing this apparatus. So first of all, we're going to consider the pressure at which the reaction should be run. You remember here that in Le Chatelier's principle, when a reaction is in dynamic equilibrium, if you change the conditions of that reaction, then the reaction will move in a direction which opposes the change that you make. So in this particular case, we want to increase the yield of ammonia. We notice that we've got 4 volumes of gas, or 4 moles of gas on the left, and 2 volumes of gas, 2 moles on the right. And so the greater pressure is on the left-hand side of the equation. So if we increase the pressure, the reaction is going to move in the direction which causes a reduction in pressure. So by increasing the pressure, we will favour the forward reaction. Okay, so that's what this apparatus is doing here. This is a compressor, and that's going to increase the pressure of the gas to 200 atmospheres. So inside this section of the apparatus, the pressure of the gases is increased up to 200 atmosphere. So we've got very high pressure. The reaction moves in the direction to oppose that increase in pressure, and that is the direction that results in the smaller number of moles. And in this case, that is the forward reaction, which is what we want. That gives us ammonia. Okay. Now we consider the temperature aspect. Now this ammonia reaction, the forward reaction in this case, is exothermic. Okay, that means delta H is negative, which means that heat is released in the forward direction, which means that heat is released as ammonia is formed. Now then, what that means is that actually what you really want to do is to cool down this chamber. That's to say, to reduce the temperature in order to favour the forward reaction. Remember, just spelling it out again, that Le Chatelier's principle states that any changes introduced to a reaction in dynamic equilibrium, that reaction will move in the direction that opposes that change. So if I reduce the temperature in the chamber, okay, then the reaction will move in the forward direction so as to produce heat, so as to increase the temperature. Okay, so ideally what we really want is to cool down the chamber. However, there's a problem with that. The problem with that is that if you reduce the temperature of the chamber, then you radically reduce the reaction rate. That's to say, the reaction will start going too slowly. So you've got to have a compromise between having a high yield at a low temperature and a faster reaction rate at a high temperature. And so the compromise temperature is around about 450 degrees Celsius. Okay, so we want high pressure and a temperature of about 450 degrees Celsius, and to assist and to help speed up the reaction rate, we're also going to use a catalyst in this chamber, and the catalyst that's used is iron. Okay, that acts as a catalyst. So we have catalyst in our equation is iron, and so you've got this series of iron beds here acting as a catalyst to help speed up this reaction. Just to try and explain again this business of this compromise, you can think of it like this. At a lower temperature you may get a higher yield, let's say a 20% yield, but it may take you 1 hour to obtain that 20% yield, because at the lower temperature the rate of the reaction is slower. The particles are moving slower, there's less probability of a collision, and the energy on impact will be less because the temperatures are lower. Okay, so at your compromise temperature of 450 degrees Celsius, we've increased the temperature. That means we've got a poorer yield, because remember that the reaction is exothermic. So an increase in temperature will tend to favour the backward reaction. Okay, so you get a smaller yield, but you get that smaller yield in a much faster time, for example 20 minutes say, okay, because at the higher temperature the reaction rate is greater. So in that sense what you're getting is a 30% yield in an hour, because 320s are an hour, so 3 times 10% is 30%, rather than this 20% yield. So it pays to run the apparatus at this higher temperature. Okay, just to finish with, we remember that we've got a reversible reaction going on inside this high pressurized heating chamber here. So what that means is that at any one moment we've got a mixture of nitrogen, hydrogen and ammonia. Okay, so what we've got to do is we've got to separate the ammonia from the nitrogen and the hydrogen. Okay, so here we've got nitrogen, hydrogen and ammonia gas, and what this apparatus does here, this is a condenser. This is going to cause the ammonia, which has a higher boiling point than nitrogen or hydrogen, to condense into a liquid. So you're going to get liquid ammonia being tapped off from this condenser unit, and then the nitrogen and the hydrogen are then recycled around the system, and the ammonia is being removed from the system through the condenser and tapped off here. Now the advantage of removing ammonia gas is that we're reducing the concentration of the ammonia gas here in this reversible reaction, and again Chatelier's principle will then come into action once more, because if I lower the concentration of this gas here, then the forward reaction will be favoured so as to produce more ammonia gas. Okay, so removing ammonia gas from the mixture reduces the concentration. The Chatelier's principle then kicks in so as to favour the forward reaction, so as to increase the concentration of ammonia gas in this chamber. So we're lowering the concentration of ammonia gas, and that favours the forward reaction. Now with regard to the uses of ammonia, ammonia has a number of very important uses, industrial uses. We'll look at that in the section on industrial chemistry.